the Zoom. Alex, if you want to just unmute and introduce yourself really quickly.
Hi, everyone. I'm Alex. I'm faculty at Grand Valley State University in Michigan.
Great. And Emily will be joining us a little bit later. She's a faculty at Michigan State University, but she's in the ISAL board meeting right now. So our objective for this tutorial is to get through a very brief introduction to the concept of phylogeny in evolution, and then transition to an interactive kind of hackathon style series of code challenges that we're going to be running through Google Colab. So I'll go ahead and get started and work through this brief introduction to phylogenies. Get to the next slide. So a phylogeny is just a record of ancestry among replicating individuals. So a really intuitive way to think about phylogeny is just building up a tree structure based on parent-child relationships. So we can track phylogeny at this individual level by connecting agents based on their ancestry. However, phylogeny can also be defined at higher levels of abstraction. So if we classify our agents in this simulation by some phenotypic trait, here this blue star, we can kind of collapse them all to one node. And if an offspring is created from one of our blue star phenotype individuals, we can draw that connection out between these more abstracted nodes. So a really important concept is defining this idea of what we consider our operational taxonomic unit. And so in this example, we've defined this phenotypic trait, the blue star or the yellow lightning, or this green diamond as our operational taxonomic unit. There's two main types of phylogenies that you'll encounter in A-life simulations, from asexual systems, asexual phylogenies, which are just tree structures. But if there's the presence of sexual recombination within a simulation, the phylogenetic structure can get a lot more complicated and become kind of a more general graph structure. However, you can still typically if you have subpopulations that become separated and no longer interbreed, you can kind of, at a higher level abstraction, draw out roughly an asexual phylogeny of the relationship between these subpopulations that are interbreeding. So there's a bunch of different reasons why tracking phylogeny is useful for A-life and digital evolution. It's not just useful for getting a explicit record of what happened in the simulation, but we can also get more general information out of the phylogeny. We can, for example, understand information about the presence of selection pressure, spatial structure, and ecology. This diagram is from some recent work that I did with Emily, looking at how different evolutionary conditions create structure that we can measure through phylogenetic statistics. Phylogeny is particularly useful for detecting ecology, especially where if we have long-term coexistence between branches because of stable coexistence, stabilizing factors, we expect these to show up in our phylogeny. So for example, here on the right, we have a phylogeny that only has one long-term branch, and on the left we have, or I think I have that backwards, we have long-term kind of evidence of long-term coexistence between four clades here. So I'll hand it over to Jack for these last slides.
So phylogenies also have a lot of potential performance gains as well in your evolutionary algorithms, because there's a lot of similarity between solutions in the phylogeny. Typically, you can use one relative of another solution as an estimate of that solution's performance. And so if you've evaluated a parent on some test, you can also use this information, or if you've evaluated the grandparent or so on a test, you can use this as a rough estimate for how a descendant will perform on this test. And if you are working with a large number of tests, this can actually save you a lot of compute because you don't need to evaluate every single solution on every single test. And then for the coevolutionary case, this is some work that I presented yesterday. You can also use this for co-evolving populations. And so you can use the relatedness between tests to approximate how an individual will perform. And so if you think about how your parent did against an opposing population's parent, you can use that as a rough estimate for how you do against the opposing population's parents' children. And I'll hand it over to Alex for this last slide.
Hi, everyone. So for the bulk of this tutorial, we really wanted to spend our time encouraging you to incorporate phylogeny tracking either in your own system, or if you just want to play around with some toy notebooks we've made. I think Jack has a Julia notebook, and then we also have 2 Python example notebooks where you can incorporate, I think, Jack's phylogeny tracking library into a Julia notebook, and then there's the PhyloTrackPy library you can incorporate into the Python examples. I'll go ahead and share my screen. Ooh, you cannot show. Matthew or Jack. Okay, cool. Share my screen. So here's an example of one of these sort of notebooks that you can play around with. I think they are all available on GitHub, and we'll share the other screen in a minute, which has the link on it. But if you go to the GitHub repository and you go inside of this notebooks tab or folder, there's a couple of different notebooks that you can open up. If you click on any of them in here, you should be able to, there should be a link. So like if I click on maybe the synchronous example, should be a link to Open in Colab, so you can just click on that link and it'll take you over to the notebook Open in Colab where you can play around with it. And what these examples have in them are just sort of bare bones, really simple toy example of the Python ones. There's a synchronous generations example, so that's more of a classic evolutionary computing setup where your generations are synchronous. And then there's also an asynchronous generations example, so it's a little bit more of a classic digital evolution setup. And inside of these notebooks, we have like bare bones basic implementations of basically the one max problem. But inside of it, we've added these sort of tasks. So to give you the opportunity to play around with, okay, well, if this were my system, how would I add phylogeny tracking into it? So in the Python example, so like there's the first thing to do is to go figure out, well, how do I initialize PhyloTrackPy's phylogeny tracker? And then, okay, well, once I initialize it, how do I add my initial population to it? How do I update the systematics objects to update to the current generation, etc. So you should be able to sort of, again, the code should be fairly simple. You should be able to follow the tasks. And of course, we're here to help you answer questions. If you just want to skip ahead to a working version, we have those as well. So if you don't want to play around with it yourself and you just want to look at something complete, inside of this notebooks folder, we also have complete versions of all of the notebooks. So if I go to the async, completed async, all of the code for all of those tasks is here. So if you can't figure something out, you can also reference this. Let's see. I can stop sharing my screen. I think we'd really so you can either use those notebooks, but if you want to take a swing at implementing phylogeny tracking in your own system, We're also super interested in supporting that as well. So it's sort of a choose your own adventure for the tutorial, and we're here to support any of the adventures that you choose. Do you all want to share that other slide that had the links on it?
Sure. Thanks, Alex. Okay. Oh, let me share my screen because I don't think oh no, I am sharing my screen. Okay, there we go. Well, I'm not sharing it on Zoom though. Hold on. Let me go back to Zoom real quick. But I caught that. Okay.
Oh, and real quick, so for online participants, I know the webinar or Zoom format is a little awkward to interact. So I will post I think if anyone online wants to get help with anything or sort of interact a bit more than what we can do in the sort of Zoom webinar mode, we'll hop over to the A-Life um, Discord servers meeting room Sigma, and I will hang out in there. Um, we'll see how much I can hang out on both the webinar and there, but I'll go hang out over there. So that'll be a really good place. Like you can share your screen and we can step through things.
Let me just pull up the repo on the screen as well. Danish keyboard is really hard to use. So as Alex mentioned, this is the GitHub repository. I just wanted to do a brief overview of the Julia notebooks before we get started. So if you click on the notebooks folder, so the Julia notebooks do not have the open in collab button. I just wanted to make that clear. So if you want to open the Julia notebooks, there are links over here. So just click this link and this should be able to pull it up. I'm sure something will go wrong, but oh, look at that. There we go. Okay. And it's recommended for Julia to use the Colab notebook specifically, just because, well, actually, just out of a show of hands, how many of you have actually used Julia before? Okay, some people, some people. Uh, but yeah, if you're interested in using the Julia notebook, that's an option. But if you don't have Julia installed on your system, it can eat a lot of battery if you're on your laptops. So if you want to preserve your battery life for the rest of the day, you can just use the Colab notebook. And this is also tested with the installation and everything. And so you shouldn't have any problems with that. But you will have to install the Julia programming language in your Colab notebook, and then you will have to refresh the page to actually load the kernel. But after that, it should be smooth sailing. Okay, so here is the link to the GitHub repository. I'm not sure if any of you want to try to use your laptop cameras to capture this QR code, but you're welcome to try. There's also a shortened URL link over here that has the materials for the tutorial. And these challenges shouldn't be too complicated. They're pretty straightforward. So you might have some extra time left over. In the Julia notebook, there's an optional challenge. But if you finish early, you're welcome to leave and go to another session and attend a few other talks if you want.
Oh, and one more thing. Depending on interest, and from Zoom, it's hard to see who's in the room, how many people are in the room. If folks do get phylogeny tracking working in their A-Life system in the next couple of weeks, couple of months, and are interested in putting together a sort of workshop report, just talking about basically reviewing phylogenies across A-Life systems, I think we'd all be really interested in organizing that. So if you do and you're interested, chat with us after the tutorial, send us a message, email us, contact us, and we'll try to organize something.
All right, we'll go ahead and get started.
Should I repeat the question for online people, or should
Yeah.
you summarize? Or
I can summarize. So the question was about the operational taxonomic unit in the slides, about how that phenotype can be defined in kind of non-trivial systems like Avita. In Avita, a really typical way to define the phenotype is if you're rewarding like the logic tasks as kind of the set of logic tests that you're doing, and kind of choosing an appropriate definition that gets you the semantic information that you're interested in your system is like going to be really uh, application dependent. But you can also, like you mentioned, you can also define these taxonomic units in terms of genotype. And so you can just kind of lump all of the organisms that are exact clones of each other into a single node and kind of coarsen a little bit from direct individual level tracking.
Yeah, I would definitely advocate for the second option because, well, if you want to study the existence or not of neutral plateaus and stuff on landscapes, if you want to see what kind of mutations may lead to some mutational bursts, if you want to, I mean, the genotype is interesting, okay, but then you usually have a deterministic mapping from your genotype to your phenotype. So if you have the genotype, you do have the phenotype, but the contrary is not true, not necessarily true. So I think you lose quite some information grouping by phenotype rather than genotype. So I'm not saying everybody should do it on the genotype, but maybe everybody should ask himself the question, what level should I group upon if I group?
Okay, now this is going through. I was just saying, if you preserve the phenotype information, you can always coarsen later in post-processing. So, yeah, you probably want to think about preserving some flexibility for the types of changes in your analysis that you might want to make later. Yeah. Are there any other questions or, yeah?
Sorry. Well, on that subject specifically, I'd like to take a more drastic view, and I'd like you to try and convince me that we should even consider the phenotype. What advantage will it bring? Because it seems to me that we are going to first do the exact same thing as phylogenicists have done before we had access to genetic material and say, oh, those two things look alike, so they should belong together. And then we'll get to the genomic comparison and we'll see that they have actually a very divergent history. So because I missed the beginning, we are working on a video, so I'm not sure how true it is in this context, but I'm guessing we're not just talking about Avida, but phylogeny in general. So can you convince me that phenotypic grouping makes sense?
Yeah, absolutely. So one argument potentially in coarsening by phenotype and runtime is the space and time savings, where if you have a really long running simulation, and even if you're pruning your phylogeny, so you remove the extinct lineages from the records, you'll still have accumulation over the course of your run. And so potentially you could run into performance trade-offs there. And with respect to kind of the semantic information that you're capturing by coarsening at the phenotype level, I know there's some really interesting use cases for this in I don't know if you've heard of the modes toolbox that Emily and some of her collaborators worked on before, but there's kind of analyses in there that specifically look at change at higher level phenotypic traits over time. And so if you're specifically targeting those kinds of analyses, it can be convenient to coarsen by these phenotypic traits you're interested in applying the modes toolbox to. Although you can track at a finer level and then coarse in later before you run stuff through those analyses.
So to summarize and make sure I follow, the argument is to save computational resources and space by using coarser phenotypic. I need coffee. Phenotypic characteristics.
I think that's a fair characterization of kind of because you're strictly losing information. So it's, you can always, for analyses, you can always coarsen later. So the only reason that you would want to coarsen at runtime is for performance or memory use or just convenience, if you specifically know what analysis you're going to be doing.
But in any case, you will have to coarsen, right? Because we have access to everything.
Everything, including the exact computation. So from simply, if my system is able, sorry, to answer the question. So you don't have to. In Evel, if you have the first generation genome and you have only the tree, actually, even if you you prune completely the tree to have only the winning or the lineage of the individual of interest, you can reconstruct the whole history of the genomes that went through the whole lineage for millions of generations. So you don't have to, but it is costly. It does take a lot of space, even on disk, it's big, but then you don't have to. It really is a trade-off. What do you want? What questions do you want to ask your model? And what do you need to answer these questions, I think.
And then one other comment that I wanted to make is that there are some cases where you are doing a very long-running evolutionary simulation, and you can get these coalescence events, basically, where your entire population becomes descended from one common ancestor, essentially. And depending on what kind of analyses you want to actually do, you can actually strip out all the phylogenetic information from that most recent common ancestor upwards if you don't need it, just because if you really care about like your population level statistics, then that's all you really need, because then it's just basically a very long path from the most recent common ancestor back to the initial individual if you're working with asexual phylogenies. So there are other ways that you can reduce the memory usage as well, but you can, by also pruning branches that no longer exist, you can avoid having to keep a lot of the memory that you would otherwise need, and you can free that up, basically.
One other aspect of performance that I just realized or remembered was if you use the PhyloTrackPy tracking framework, it supports calculation of phylogeny summary statistics at runtime. And so if you're going to be wanting to compute those statistics over the coarsened phylogeny, it can be really convenient and save a lot of time to compute those on the fly as the simulation is running, and then save out those like a time series of those summary statistics is kind of one way you can maybe even go even further in coarsening and summarizing. Any other questions or discussion? This is great.
Yes, 4 hours about that, but maybe that's not the point.
Yeah. Cool.
Okay, so yeah, feel free to get started on the notebooks. Let us know if you have any questions or any technical difficulties. Some of the notebooks have had some minor last-minute changes to them, so there might be an unforeseen bug or two. So if you're working in the Julia notebook, you can call me. And Alex will be available for the Python notebooks, and I believe Matt would also be able to help with that as well. But yeah, thank you.